All righty, folks. Hello, hello, hello. Good to see you all today. All right. It is a Saturday morning for me. I don't know about you all, but we're going to be finishing up kind of this idea of extrema and concavity. And then the next few days, we're going to be putting it together in different scenarios. But today, we're going to kind of make sure we finish up how all these first and second derivatives, how they all relate to each other. So we're going to go back. Let's take a look at our graph we've been starting the last few days off with. And one final thing we need to bring up here. Oh, there we are. And you guys, by now, you probably know that I'm going to throw a relative maximum on there. And I'm going to throw a relative minimum on there. And by now we know exactly what a relative max is. It's where the graph goes from increasing to decreasing. It's when the first derivative changes from greater than to less than. And then also right here we have ourselves a relative minimum. And that's when our graph goes from decreasing to increasing. It's when our first derivative goes from a negative derivative to a positive derivative, positive value. But notice what happens here. We also had this idea that we talked about last class called a point of inflection, and that's where our second derivative changes signs. So in other words, we talked about this idea that this area right here, when the graph is kind of opening towards negative infinity, it's opening down. We had this idea that this graph was concave down. And what that meant for us is that it meant that our second derivative was less than 0. And we have this other idea. So that point of inflection, it breaks up the concavity. So we had a portion of that which was a concave down, but we had the other portion of that that was concave up. So let's write that in there just for the fun of it. This section that is concave up. And again, our concavity is broken up by the point of inflection, so the POI. So now usually we describe a relative extrema by it where it changes from positive to negative, the derivative, or when the derivative changes from negative to positive. But if you notice, those relative extrema are also related to concavity. It's also related to the second derivative. In other words, if we have a relative extrema, so in other words, if we have that horizontal tangent line, in other words, if this value right here, we'll call it C, if it had a derivative equal to 0, and it had a second derivative that is less than 0, well, that would also have to indicate that we have a relative maximum. If we had for a relative minimum, have another horizontal tangent line. If we had this idea of a first derivative that had was equal to 0. Let's call this one, I don't know, how about we call it n? So f prime of n equals 0. Just random, some random x value, it doesn't matter. But it was concave up on that region, that would have to be then a relative minimum. So we can test concavity more than just using a first derivative. We can also test it with the second derivative. And that's what we call the second derivative test. So we had a first derivative test. Turns out we have a second derivative test for relative extrema. So first part, okay. At some value c, if f of x has a relative maximum at that point c, f of c, again, remember, absolute extrema is a value, it's a function value. Relative extrema and points of inflection, those are points, those are locations. So anyways, back to our problem here. At x equals c, f of x will have a relative minimum at that point if the first derivative equals 0 and the second derivative is less than 0. Second part to this is it will have a relative minimum at that point if the first derivative equals 0 and the second derivative is greater than 0 at that point. And I should probably make those C. We're going to evaluate it for the C value. There we go. I feel a little better about that. And then just like with the first derivative, sometimes it doesn't work. Sometimes there is no relative extrema at that value. Although sometimes there could be for the second derivative test, it just doesn't work. Sometimes the second derivative test isn't going to work. So it's quicker to do the second derivative test, but here's the drawback of it. Sometimes it doesn't work. That's a pain because then you got to go back and do the first derivative test, which you could have just done in the first place. So realize that the second derivative test isn't always going to work for us. It'll work a lot of the time, but not always. And if it doesn't work, no harm, no foul, go back and use the first derivative test and see, does it work there? Or maybe it just didn't have a relative extrema. You can't tell if a point just doesn't have a relative extrema using the second derivative test if it fails. You got to go back and do the first derivative. So this is what we're going to be playing today. We're going to play with this idea of a second derivative test, okay? So how does this work? Well, let's come back here. Come back and revisit some of our favorite functions from before. We'll try it. Determine the relative extrema for f of x equals 2x cubed minus 3x squared minus 12x plus 1. And again, if it doesn't tell you, you can really do it any way you want to. I'm going to choose to do this, though, with the second derivative test. All right, friends. Now, you're probably bracing yourselves because you know what I'm about to do here. Whenever we do this, we're going to say what we're going to do, and then we do the work. When we're done, we're going to say what we did. Seriously, the song, you should have it stuck in your head by now. So we are going to start off and say what we're going to do. So relative extrema will exist, can exist because we're not using the first derivative test this time, can exist when f prime of x equals 0 or when f prime of x is undefined. So I'm just going to set it up to, it's a little bit different sentence than I've used before. It still will work. Notice, but the biggest issue and change on it is I didn't say will exist this time. I just said it can exist. So it gives me permission still to deal with the first derivative and then deal with setting it equal to 0 to find those critical numbers. Okay. But the big issue here is I didn't say will exist this time because I didn't talk about it changing signs. I just said it can exist, so I can write one sentence instead of two. So we said what we're going to do. Now we're going to do the work, friends. Whoop! A little derivative action. Here we go. Let's see, look at that. Yeah, I'm telling you, add sound effects to your math. You will be having so much fun. I had a girl tell me a few years, no, it wasn't a few years back, it's probably like 10, 15 years back. She was doing sound effects for her math problems in her room, and her parents got a little nervous, so they actually took her door off her bedroom. I don't think parents would do that anymore. Now that we value your privacy a little bit more, but I told that girl, then probably better stop doing sound effects when doing your math, man. So. All righty, so we can go ahead. We factored all the way out. Whoop. We're going to get ourselves our two critical numbers, and amazingly, it's still the same critical numbers we had before. Go figure. Now, if I'm going to do the second derivative test, I don't have to say that I'm going to do the second derivative test. That'll come up when I explain what I found. All I have to do is just go ahead and do it. So I got my critical numbers. So on the second derivative test, then I'm going to just go ahead and grab it. So the second derivative would be 12x. Go back to your first derivative and take the derivative of the derivative, minus 6. And you'll see the second derivative test so much faster. But again, the problem with it is that it doesn't always work. So 12 times 2 minus 6. That would be 18. So since I have a positive second derivative at that critical number, that tells me that I have a relative min, which we've already seen before. And then I'm going to do my other one, f of negative 1. 12 times negative 1 minus 6 is a negative 18. So I have a negative second derivative. By the way, just a coincidence that they ended up being the same value. So this tells me right here that I have a relative max because I had a positive second derivative. According to the second derivative test, this told me that I had a relative min because I had a negative second derivative. And just like before, we need to also make sure that we go through and then find what those values are. So it worked, but I need to know what f of 2 is. So I'd have to go back and plug 2 now into the original function to get what y value is associated with it. Because again, points of inflection, relative extrema, those are points. I'm going to plug negative 1 in to the original function to get the y value that goes with, which would be 8. So I said what I'm going to do. I did all the work, and when I'm done, I'm now going to say what I found. Here we go. There is a relative minimum at the point negative 1, 8, because f double prime of negative 1 is 0. Notice, it's a lot shorter sentence before. There is a lot of great things about the second derivative test. The only issue that comes up with the second derivative test, and it's a big issue, that sometimes it just doesn't work, which is an absolute pain. There's a relative minimum at negative 1, 8 because the second derivative at negative 1 is less than 0. Also, another big thing to remember here is that you say f double prime at that x value. Because remember, it's not going to be every f double prime of x. It's f double prime of negative 1, f double prime of 2. It's only at that value. So again, here we go. Say what we're going to do. Do the work. And when you're done, you got to say what you did. All right, here we go. Let's give you guys one to try because dagnabbit, that just sounds like fun. Whoop. Determine the relative extrema for f of x equals, oh, let's see here. Let's go back to our original one we've been doing, the other original one we've been doing. Minus 20 x cubed plus 2. So we had 3x to the 5th minus 20x cubed. All right. So friends, why don't you guys go ahead and pause the video and try determining the relative extrema with that one using the second derivative test. For those of you that are still watching, this is me using magic eraser. I tell you what, your parents probably had the little white magic eraser to get all the junk off the walls. Well, this is my magic eraser right here. It's just fun. No, it just doesn't want to come, does it? We'll just rewrite that one. All righty. So by now you unpause the video. You've watched me do this as I try to get the problem reset up. So here we go. We're going to say what we're going to do. And so then we're going to do the work. When we're done, we're going to say what we found. So relative extrema can exist. There's that word can again. I'm only going to use one sentence, not two. Can exist when f prime of x equals 0 or when f prime of x is undefined. So it tells me I am going to go find the critical numbers for the first derivative. I've given myself permission. So now I get to go do it. First derivative, whoop. And remember, we take it one thing at a time. So we always just do just the first derivative first. Then we set it equal to 0 second, then we can go ahead and solve it. Don't do multiple steps at the same time. Never a good idea. The College Board gets very unhappy with that. Some of you are probably going, why do they get unhappy with that? I don't know. You're asking the wrong guy. They probably just, I think I have an idea. They want you to have some sort of clarity to make sure that you actually know what you're doing. So I get that. So 15x squared, x squared minus 4. So one more time here. 0 equals 15x squared, x plus 2, and x minus 2. There we go. So x equals negative 2, x equals 0, x equals positive 2. So we do the second derivative test here. Second derivative test. So I need 60x cubed minus 120x. And we're going to plug some values in here. So let's plug negative 2 in there. What'd that be? That'd be negative 480 plus 24. Really doesn't really matter. Negative 480 plus 24, that's negative 456. I don't need to put negative 456. If you see that it's just going to be a gigantic negative number, that works. That will work. We plug 0 in here, and all of a sudden, we get 0. Now that doesn't mean that there's not a relative extrema there. It just means that the second derivative test failed at 0. So for 0, I have to go back and do the first derivative test to make sure what it is actually going to be. And this would be a number that would be greater than 0 here. So what does this tell me? It tells me that I have a relative max when x is -2. It tells me that I have a relative min at x is +2. And this is where I'm telling you, when it doesn't work, doesn't mean it's not there. It means I have to go back and do the first derivative test. In order to know for sure, I have to go back and do the first derivative test. So we got to go take 0 and go back and do the first derivative test at x equals 0. So here we go. I'm going to pick my test values again. -1 and +1. Now at the first derivative test, you do one test, you know exactly for sure what it is. Second derivative test, yeah, it's faster unless this happens, unless you get a value that you don't know. So now we're going to go back and we're going to plug it into the first derivative. So plug these into our first derivative. If I plug -1 in there, I'm going to end up with a negative value. So that means this region, it's less than 0. If I plug +1 in there, I still have a negative value. So now I know for sure, since the derivatives did not change signs, they did not change signs here, there's going to indeed be no relative max here, or no relative extrema. You may think that with doing the second derivative test, but again, sometimes they will be. You just have to go back and figure it out. So we know we have a relative max and relative min at f of -2 and f of 2. So we go back and we plug those back into the original function, figure out what y value is associated with them. So that'd be 66 and -2, +2. Apparently I wanted to write -2 twice. I'm feeling in a negative mood today. I'm not really sure. And -62. So we said what we're going to do. We did the work. When we're done, we're going to say what we did. There is a relative maximum at f of at -2, 66. And actually, I forgot to put something on the last statement. Some of you guys maybe noticed it. We're going to make sure we don't forget it this time. I do still need to say it equals 0. And because remember, that's what the second derivative said. It said that the critical number equals 0 and you test the values. That was 0. So I do need to make sure I have both parts. Say the first derivative is 0. Say the second derivative was less than 0. So I forgot to put the first derivative equaling 0 the first time. But you guys being the smart math people you are, I'm sure you saw that and caught that for me. If not, no harm, no foul. We got to fix here. So f prime of 2 equals 0. And the second derivative is greater than 0. We did not have a relative extrema at x equals 0, so we do not need to worry about it. Now, if it did say if the critical number doesn't work, explain it, then I would need to go through and explain that. But it just asked me to find the relative extrema. So remember, for the relative extrema, you got to make sure you do two things. Say the derivative is 0, and then say the sign of the second derivative. Say the derivative is 0, say the sign of the second derivative. You got to say two things when you're doing the second derivative test. All right, well, I'll tell you what, let's put this all together now. All together now. All together now. All right, so given a function, I'm going to have you guys, given a function, let's make that black. Determine the following f of x equals 2x cubed minus 3x squared minus 36x plus 5. Determine the following things. Let's see if I can get my head out of there. There we are. I'd like to know, when is it increasing? I'd like to know when it's decreasing. I'd like to know when it's concave up. I'd like to know when it's concave down. Love to know what the relative maximum is. Love to know what the relative minimum is. And let's go ahead and finish off with the points of inflection. All righty. So I'm asking you guys for a lot of stuff. So when we go through and we say what we're going to say here, we got to make sure that we talk pretty much set it up for the whole rest of the problem. Let's see, I just realized I did not put my exponents on that. There you go. And actually, you know what? Why don't you pause the video? Why don't you go and pause the video, friends, and see if you can, how far you can get on it. Set, go, pause it. All right, let's see how you did, friends. Let's see how you did. Whoop. All right. F of x is increasing when f prime of x is greater than 0, and decreasing when f prime of x is less than 0. Furthermore, relative extrema will exist when f prime of x changes signs. I see my typo. I'll get it in a second, friends. All right. F of x is concave up when the second derivative is greater than 0, and concave down when the second derivative is less than 0. Points of inflection will exist when the second derivative changes sign. So we literally go through here and we set the whole problem up. All right. Set the whole thing up. All together now. All together now. We'll come back and give ourselves room as we need it. All right. So we said what we're going to do. Now we're going to come back and we're going to do the work. So I gave myself permission to deal with the first derivative. So 6x squared minus 6x minus 36. Set it equal to 0. And then we factor it. So 0 equals, I'll pull out the 6 there. And this would have gone to x minus 3, x plus 2. So we have x equals 3. And x equals negative 2. Now, friends, you can do the second derivative test if you want to. I personally usually stick with the first derivative test because I get really frustrated. It's just my own pet peeve. I get really frustrated when I do the problem and the second derivative test fails, and then I got to go back. I know that it's faster. It's just own my own gut feeling. Now that being said, when I also have to talk about increasing and decreasing domains, I also like to talk about stick with the first derivative test. So there we go. I got to pick some test points. Let's try -3. Let's try, how about 0? And let's try 4. So when I plug these in to figure out what's going to happen here, I get this first derivative is going to be greater than 0. So that means it's increasing on that domain. If I plug 0 in here, I'm going to get a first derivative that's less than 0. It's decreasing on that domain. And by the way, the College Board won't ever grade your tables. All right. You do the table for yourself to make sure that you know what's going on here and organize your work. But the College Board, they won't grade it. So increasing, it was decreasing, it was increasing. That means then I have a relative max here because I went from increasing to decreasing. I went from a positive derivative to a negative derivative. And this means that I was a relative min here. So all I'm doing is I'm just setting up my work so when I come back and look at this later, I can type up the entire thing. And then I also need to know those values, those points. So f of 2 equals, that was a -2, sorry about that. So I'm going to go back, plug it into my original function. F of -2 would be equal. Did I factor this wrong? No, I didn't. Plugged it wrong into my calculator. Oh no, friends. I guess we're going to go through the long way to figure it out. All right, f of -2. I plugged it in wrong in my calculator. That is never good. All right, f of -2. So I'm going to get 16 minus 12 plus 72. I'm sitting here looking at my numbers I got. I'm going, oh man, I plugged in the wrong number. It happens. All right, let's see here. If I plug 12 in there, -12 plus 72 is 60. 76, looks like it's 81. I could be wrong, but just eyeballing it, I believe that's 81. And then I'm going to plug 3 in here. All right, that's that. 54. 9 minus 27. 180, that would be 216. Plus 5. All right, here we go. So I got 27. I got 32. 186. -184, I believe. Again, could be wrong. You don't need to post in the numbers if I have the wrong number. I'm just speculating here. 27, 32, 32. So that's 188, 184. Actually, I think it's -184. If I had to look at it. Again, don't worry about putting in the comments what the numbers are. They're about there somewhere. All right. So we did our first derivative. Now we're ready to move on to the second derivative and deal with concavity and points of inflection. All righty. So we have 12x minus 6. Set it equal to 0. I get my critical number now for my second derivative. So x is 1/2. So I'm going to go and test my second derivative here. Pick my values to test. Let's try 0 and 1. Those seem like the easiest. When I plug in my 0 into my second derivative, I get a negative value. So it's concave down there. When I get into my one in there, I'm going to get a second derivative that's a positive value. So that tells me that it is concave up there. So I'm concave down. I'm concave up. And that means I had a point of inflection here because it changed concavity. And then I plug it in, friends, to get the actual value that goes with. Luckily, I plugged this one in because that would have been ugly. 1/2 equals negative 27 hazard, negative 13.5. All right. So we said we're going to do. We did all the work. Now we're done. We're going to say what we found, friends. Yep, going to say what we found. F of x is increasing from, where is it increasing from? Negative infinity. I'll have to come back to that in a second. To -2 and -3 to infinity, because f prime of x is greater than 0 from negative infinity. I'll write the rest of that in here in a second because I'm running out of room here. Decreasing. F of x is decreasing from -2 to 3 because f prime of x is less than 0 from -2 to 3. Concave down or concave up. F of x is concave up from 1/2 to infinity because the second derivative is greater than 0 from 1/2 to infinity. F of x is concave down from negative infinity to, because it is less than 0 from negative infinity to 0.5. Relative maximum at, where was it? Negative 281. Because f prime of -2 changed from, and I'll say where it changed from here in a second, relative minimum at 3 negative 184, because f prime of 3 changed from, and I'll say where it changed here in a second. And last and certainly not least, point of inflection at 0.5, negative 13.5, because f prime of f double prime of 0.5 and let's see here. I'm going to need a little bit more room here, aren't I? That's fine. We'll make it work. All right. Let's go through and try to fill these out here. So negative infinity. It's increasing from negative infinity. And infinity. On your paper, you'd have just a tiny bit more room than I have here. So you would have been okay. That should be a positive there. All right. Good. Concave up from 0.5 to infinity. So we said what we're going to do. We come all the way through. We do the work. And when we're done, we say what we found. Don't know why I made that a negative. Change from greater than 0 to less than 0 at x equals -2. I'll use a different colored pen here on this one. From less than 0 to greater than 0 there we go, at x equals 3. And the point of inflection changed from sign, the f double prime change signs at x equals 0.5 or 1/2. Whew, we got it all in there. All righty. So f of x is increasing from -infinity to -2 and +3 to +infinity because f prime of x is greater than 0 from -infinity to -2 and 3 to infinity. F of x is decreasing from -2 to 3 because f prime of x is less than 0 from -2 to 3. F of x is concave up from 0.5 to infinity because the second derivative is greater than 0 from 0.5 to infinity. And you guys can see the rest of it here. Relative maximum at -281 because f prime of x changed from f prime of x greater than 0 to f prime of x less than 0 at x equals -2. Relative minimum at 3 -184 because f prime of x changed from f prime of x less than 0 to f prime of x greater than 0 at x equals 3. Point of inflection at 0.5 -13.5 because the second derivative changed signs at x equals 1/2. So all that being said, friends, we can tell a lot about a graph. All we need to do is remember to first say what you're going to do. Second, do all your work. And third, when you're done, say what you found. And we can tell a lot by a function now that we know how to do first and second derivatives. All right, friends, good luck with that. And I will see you guys a little bit later, and we can talk more about this tomorrow morning.